Let's now do another example where we use the definition of the limit to verify a limit or to prove that a limit is holds. So the example we want to look at now is that lim 2n squared minus 3n plus 5 divided by n squared minus 9 is equal to, and an important point here is that determining the limits in themselves is usually not that hard. Proving that they hold using this n epsilon definition is or can be. But what is the limit here? Well, when n becomes huge, it's 2n squared that completely dominates up here. These terms don't do much of a difference. The 5 certainly doesn't, and 3n does not do much. And similarly down here, the 9 does not matter at all. So we have 2n squared divided by n squared when n becomes really huge, so the limit here has to be 2. But how do we prove this? So let's write up the definition first. So we can take the definition here. So lim n goes to infinity, a n is equal to L, if for every epsilon bigger than 0, there exists a capital N such that n bigger than capital N implies a n minus L less than epsilon. This is what we need to prove. I can mention here that I don't really write out this part that often. I often forget it. It's implicit here. Whenever n is such that n is bigger than capital N, this kicks in. But I really should write out this part too. Now, so solution or proof, you could say. So as we always do, we start out by taking epsilon to be an arbitrary number, fixed but unknown. And then we consider this expression. We try to figure out when is this guy true, okay? And in doing so, the value for capital N will pop out. So we consider an minus L, and in this case it's 2n squared minus 3n plus 5 divided by n squared minus 9. And once these expressions become fairly complicated, don't put in the epsilon here at the beginning. We now want to massage it, change this, manipulate this until this becomes sufficiently well-behaved or nice, and then we'll insert the epsilon. So first thing here is to put on common denominator like this. We'll try to simplify in the numerator here. So this kills this, and then we have the 3n here with a minus, and then we'll have plus 23. Down here we'll have n squared minus 9. Now, an important detail here, which is a bit shocking when you first start doing these things, is that no one is telling us here to find the optimal capital N. No one is telling us to find the smallest or the first capital N for which this happens. We're just asked to find some capital N. If we say that, well, for some reason, for some technical reason here, we won't consider capital N's that are smaller than 10, then that's perfectly fine. As long as we find some capital N that works, we are done. We satisfy the definition. So the first thing we can do here now is try to take care of this absolute value. It's the n here that's going to grow, so this is going to be big, meaning that this is the unimportant part. So let's here use the fact that if I take the absolute value of a difference like this, then it's the same as if I do this. So the order of the difference inside of an absolute value does not matter. So what this means here is that I can change the minus sign to the 23. So I can put here 3n minus 23 like this. And notice here, when n is strictly bigger than 3, this guy is positive. And when n is 8 or bigger, then this is positive. So here, I now impose a restriction on my n to say that it's bigger than or equal to 8. Since there's a strict inequality here, I'll say strictly bigger than 7. And then both this expression is positive and this expression is positive. So I can take away the absolute value. Yay! That's good. The next thing one can notice is that I'm actually now allowed to make this thing bigger without necessarily losing this, this game I'm playing here. So if I'm just dropping this 23, I'm getting a bigger expression. Of course, this thing here is bigger than this thing. But if I know that this thing is less than epsilon, then this guy is less than epsilon. Hence, this guy is less than epsilon. So I'm still in good shape here. Now I need to understand what to do with the guy below. So let's factorize him. Several ways you can take care of him. One way is to factor him. And now what we can see here is that, well, if I drop the 3 here, this thing becomes smaller. So this becomes bigger. So let's drop the 3. I'm getting here 3n divided by n times n minus 3. And notice I'm writing less than or equal here. clearly it's a strictly less than. It doesn't really matter too much, but if it makes us happy, we can put the strict here. Similarly, I would have a strict inequality here. But when I have a chain of equalities and inequalities, it's enough for one of the inequalities to be strict for the resulting, so the overall inequality to be strict. Okay, so now I really don't care if this is strict or not. Here, this cancels against this, so now I'm left with 3 divided by n minus 3. This thing here is simple enough for us to solve this inequality here. So now I'm throwing in the epsilon and moving things around. I see that this inequality here is the same as 3 divided by epsilon is less than n minus 3, which is the same as saying that 3 divided by epsilon plus 3 is strictly less than n. And now this thing here is my capital N. In this case, this is not the best choice of capital N. There are probably smaller capital N that will work, but this is a choice of capital N that works. How do I know? Well, if my little n is bigger than this number here, which I now take as my capital N, then I know that this inequality holds, but this expression is bigger than that expression, and I'm done. Well, wait a second. What if this number here is not bigger than, strictly bigger than 7? Well, that could be. That depends on the epsilon. If someone here chooses epsilon equal to 1, then this number here is 6. So I'm not exactly doing the correct thing by choosing this to be the n. So what I'm saying here is I'm choosing this to be the n if this is 7 or bigger. But if this is smaller than 7, well, I should choose this as my capital N. So really what I need to do here is to choose capital N to be the biggest of 7 and 3 divided by epsilon plus 3, like this. Because what happens if n is bigger than the biggest of these two numbers? Well, then little n is bigger than both of them. So both this step worked and this inequality here is true. So that's a standard move. So the standard move is that when you do this computation, you can put a lot of restrictions on your n, how many you want, and then you just say that, well, in the end, let capital N be the biggest one of all of these restrictions you've put on little n, and then you won. So we can just do a numerical thing here. So let's say that epsilon is equal to 1. Well, this implies that n is equal to the maximum of 7 and 6. So in that case, 7 works. And let's take epsilon is equal to 1/10. In that case, n is equal to the maximum of 7 and, well, this will be 30 plus 3, so 33. So this would be 33. Let's maybe take a look at how this looks in Python. So first, let's take our sequence. And we saw here that 7 and 33 were our n's, so let's do 0 to 40 here. And then we do our n-axis, and then we plot. So plt plot, and we get a division by 0. So that happens, oh, it should be 9 here. Sorry, 9. And that happens at 3. So let's start at 4, just to ignore that. So now we're starting at 4. This thing looks like this, and we're approaching the limit 2. So just to make things a bit easier to see here, let's do plt ylim. Let's go from 1.8 to 2. And then let's put some tick marks here. So plt yticks at 1.9, and then 2, and then 2.1. This, and then plt grid. And then also perhaps do 2.2 here. And then let's see. So when is this sequence 1/10 close to 2? We're guaranteed that when we pass 33, this happens. So at 33, we're here, and definitely we are now within 1/10 of the value 2, but this already happened at, well, somewhere here, 15, 16, 17, okay? So this would be like the optimal capital N, but since we did a few inequalities throwing stuff away, we lost a little bit, but still we were able to pinpoint a region from which this starts to happen.